cars pulling trailers, snowmobiles pulling sleds, and stuff getting all pushed around. Let's learn physics. Solving two object problems using Newton's second and third laws, Chapter 1. Newton's first law of motion, the law of inertia. All objects at rest will naturally stay at rest, unless acted upon by a net force. All objects in motion will naturally maintain a constant velocity, unless acted upon by a net force. Okay. Newton's second law, it's the equation. Net force equals mass times acceleration. And you could write it down as a sentence like the acceleration of an object is directly proportional to the net force applied to an object and inversely proportional to its mass, or inertia. Okay, that's the second law. Now Newton's third law deals with two objects at a time. Always two objects at a time. Newton's first and second only dealt with one object at a time, but Newton's third law deals with two objects at a time. And the best statement of it is not the whole action-reaction garbage, just crappy language, don't use it. But the two objects always apply same size opposite forces to each other. Two objects always apply same size opposite forces to each other. Because equal and opposite, no, these two forces that are opposite each other are by definition not equal because they're opposite. Because force has a vector nature to it. And if they're opposite, they're not equal. So anyway, two objects always apply same size opposite forces to each other. And a lot of our second law problems require an understanding of Newton's third law because you have two objects pulling on each other, and that internal force between the two is a third law force pair. We don't call it the action-reaction law. Ugh, it's such bad language. We call it the force pair law because they're always in pairs, always in pairs. So this is a series of videos on Newton's second and third laws of motion together. Problems, lots of them. Enjoy. Chapter 1 of second and third law, two object problems. But if you're just watching through this and not stopping and solving this independently, you're doing something wrong. So please stop and solve these things all by yourself on a piece of paper and then check it. Two object problems, horse and cart problems, or also known as car and trailer problems today. A 2,000 kilogram SUV pulls a 400 kilogram trailer. Got the masses. The acceleration is 2 meters per second. Every second there is no resistive friction. Okay, when you're reading these things, you can underline stuff, write little things in the margins before you start solving the problem. Question is, what is the force that the car tires apply to the ground to push them forward? It's a friction force. What force must be applied to the trailer by the car? So two separate problems. And we're going to two objects can be treated as one for certain parts of the problem. We'll start with that. And then we'll break it up to find the tension between the two. Pick one of them, draw the free body diagram of that one. Okay, so here's the situation. Acceleration is 2 meters per second every second. There's no backward friction force. Sketch the situation first. That's a good idea. And remember, stop the problem to solve it rather than just watching me. It'll help you. Then net force equals mass times acceleration, just the whole thing as one piece. Net force, well, that would be the friction force forward on the tires on the car, and the total mass, 2,400 kilograms times the given acceleration of 2 meters per second every second, and that force would be 4,800 newtons forward, and that is the friction force. That's the only force forward on this thing. So friction force between the tires and the road, 4,800 newtons forward. Now, what force must be applied to the trailer by the car? I can pick either this one or this one to solve for the tension. Now, the tension is pulling backward on the car, forward on the trailer. That's a Newton's third law application. So I have chosen to draw the free body diagram of the trailer. Forward force, no resistive friction force, as it says here. Normal force, weight. Then net force is 400 kilograms. This is one object. Right up here, you're dealing with two objects, the whole thing together. This one down here, just it. 400 kilograms is the mass of the trailer. 2 meters per second every second is its acceleration, common acceleration. There's an 800 Newton force on the trailer. So of the 4,800 total newtons of force required to accelerate the whole system, 800 is for the trailer, and the balance of 4,000 would be exclusively for the SUV. And that 800 newtons forward on the trailer is the same as the 800 newtons backward on the car, because two objects Always apply same size opposite forces to each other. All right, second one. 1,000 kilogram car pulls a trailer, 5,000 Newton force is applied to it, and it accelerates at 2 meters per second squared. What's the mass of the trailer? What's the force applied to the trailer? Oh, you didn't get the mass of the trailer. So minor variation on this thing, and we're going to solve it. And first you start out with net force equals mass times acceleration. You know that there's a 5,000 Newton forward force. We're assuming that there isn't any friction, because otherwise we couldn't solve it. And then 5,000 newtons is equal to 1,000 kilograms plus the mass. Total mass. You're looking at the whole thing together first, right? Two objects can be treated as one for certain parts of the problem below. One free body diagram or just one system. 5,000 Newton force is the only force acting in the horizontal direction. Total mass, 1,000 kilograms plus m times 2 meters per second every second. Distribute that. 5,000 is equal to 2,000 plus 2m. Subtract. You get 3,000 newtons. Divide by 2, 1,500 kilograms. So it turns out that the trailer is 500 kilograms more of mass than the car. And what's the force applied to the trailer? Do the same thing. You can, again, pick either the car or the trailer, and forward force on the trailer, in this case, its mass is 1,500 kilograms. So the weight is 15,000 newtons because we're using W equals mg, and g is 10 newtons for every kilogram. Don't use 9.8 for the problems. It's easier to use 10. 15,000 newtons, the up and down forces balance each other. And you get net force equals mass times acceleration again, 1,500 kilograms times 2 meters per second every second. And the forward force would be 3,000 newtons. 3,000 newtons forward for the trailer, Total of 5,000, 3,000 for the trailer, 2,000 for the car. Since you probably didn't actually stop and solve, grab a piece of paper and a calculator, stop and solve these things independently and check. That'll help. A 200 kilogram snowmobile is pulling a 300 kilogram waxed wood sled on snow. Like, what about the specificity? Oh, coefficient of friction. This is all flat stuff too. The acceleration of the forward force from the snowmobile tread is, find the acceleration of if the forward force from the snowmobile tread is 3,000 newtons forward. And find the forward force pulling on the sled. All right, so again, we're going to do two objects as one and then separate. So here's the situation, 300 kilogram sled. Great sled, huh? Beautiful little snowmobile. And then the coefficients of friction. So from here, you're looking at something like this and you have waxed ski on snow. You're going to find some values like this in a given chart, or you look them up. And kinetic coefficient of friction is 0.05. The static coefficient of friction is 0.14. This is accelerating. Find the acceleration. And the kinetic coefficient of friction is that which we will use. Looking for the acceleration, write that thing down. And then, okay, so it's 3,000 newtons forward on the system, minus the friction force on the sled is going to be divided by 500 kilograms. Well, unknown. Two unknowns, one equation, can't solve it. But I do know my friction equation. And my friction equation is friction is equal to the coefficient of friction times the normal force. So over here, I have a free body diagram of the sled itself. 3,000 newtons down, 3,000 newtons up. Those two balance each other, the normal force and the weight. Forward force, friction force. This one's bigger because it does accelerate. And so just the coefficient of friction times the normal, you're assuming that it does accelerate, it does slide, so that's 0.05 times the normal force of 3,000 gives you 150 newtons. Oh, so 3,000 minus 150 divided by 500 gives you the acceleration. So 2850 divided by 500 gives you 5.7 meters per second squared of that system forward. Got that? All right, now find the forward force pulling on the sled. Now you have to pick this thing. What's the forward force? I know the friction force. Newton's second law again. So I'm going to go over here. Newton's second law, net force is mass times acceleration. Forward force minus backward force, big F minus the friction force that I now have calculated, is equal to its mass, just its mass. We're dealing with the individual free body diagram here, multiplied by the acceleration of the system that I found over here. Forward force minus 150 is equal to 1710, which is the product of those two. Add 150 to it, get 1860 newtons forward. So 1,860 newtons forward. 3,000 newtons for the whole thing, so 1,860 newtons for that, pulling back on the snowmobile, and pulling forward on the sled. That's both of those. And you need 3,000 newtons total, 1,860 for just the sled, and of that forward force, let's see, the balance is 1,140 newtons to accelerate this. Very similar to the horse and cart and car and trailer problems and snowmobile and sled problems is this. A 5 kilogram block is being pushed by a 5 Newton force. In front of it is a 10 kilogram block. There is no friction force. Again, we're assuming flat. What's the acceleration? How much force is applied to the 10 kilogram block by the 5 kilogram block? Okay, picture that in your head and then draw the little sketch of the situation on your paper. 5 kilograms, 10 kilograms, and 5 newtons on the system. No friction force between those two surfaces. What's the acceleration? And what's the forward force on the 10 kilogram or the backward force on the 5? So two objects, the 5 pushes the 10 pushes the 5. Those forces are the same size and opposite. Now, net force is equal to net force. Acceleration is net force over mass. The net force is 5 newtons on the system because there is no backward friction force. The system, 15 kilogram mass, 5 over 15 is 0.33 meters per second every second. All right, so now how much force is applied to the 10 kilogram block? I can pick the 10 or the 5 to draw the free body diagram of that, and I have chosen the 10 kilogram block. So the 10 kilogram block, forward force on it, no backward force because there is no friction. Normal force and weight, they balance each other again. Net force is mass times acceleration. Forward force equals mass times acceleration, 3.33 newtons. 5 newtons forward for that thing, and 3.33 is specifically for the 10, and the balance of 1.67 would be for the 5, no friction. The next one, a 30 Newton force is applied to the situation below. Find the forces between the blocks. Here I have to give you this situation. Here is 30 newtons, 10 kilograms, 10 kilograms, 10 kilograms. All three of those are the same. 30 Newton force is applied. Find the force, but there's no friction. So 30 newtons, 10, 10, and 10. Oh, well, if I've got 30 newtons on the whole situation, and that's 30 kilograms, there's no friction. That would mean that there's 30 for the whole thing, and then the force between these two, that would probably be 20 newtons, because it's pulling 2/3, and this would probably be 10 newtons because it's pulling 1/3. So I can think about it and like, oh, well, that's got to be 10 newtons, that's got to be 20 newtons, and then mathematically solve the problem if I needed to. Net force over mass, which is 30 newtons on the system, divided by the 30 kilograms of the system, which gives me 1 meter per second every second forward. And I can pick one of those things, or two of them at the same time. The last one, so pick this one up here, draw that free body diagram, top view if you want to. Forward force is 10 kilograms times 1 meter per second every second. And again, this is this last one. The tension forward, since there is no friction, is equal to the net force, which is 10 newtons forward. Oh, so that checks what I thought before. And then for this part here, that's this tension. So this tension is going to be on this right-hand side. And I can treat these two as one object, so that's 20 kilograms. So the tension forward at this point is applied to a 20 kilogram mass because there is no friction. So net force equals 20 kilograms times 1. Oh, 20 newtons for that? Check. Looks good. Some of these are pretty quick solutions, and you can think through them or get a pretty good idea of what they should be by thinking about them. Remember, surface friction is coefficient of friction times normal force, whenever you see that. This is second and third law, 2 object problems, chapter 1. Chapters 2 and 3 are coming soon. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.